So I thought the tradition of these tea time talks is to make some links across different subjects. That is perhaps the theme of where we are in this thing called a combination room, which probably for most people in the audience is a rather strange name for a room. I understand that there is a particular reason within the AIMR to choose that name. But in fact, for me, it was a familiar name because it so happens that if you go to the Oxford English Dictionary, you will find there is it's a rather strange example where it's a word which has only one meaning. And it's used so far, up to this point, in only one place, namely in the University of Cambridge, where it is the place in colleges where the faculty meet. In the rest of the English-speaking world, it's called a common room, but for reasons unknown, in Cambridge it's called a combination room. And the word was first used in 1650, or first recorded in 1650. And so Cambridge has got many colleges, roughly speaking 31, and you might be interested that each college, more or less, has 3 combination rooms. This, of course, is the English class system at work. So the undergraduates stay together in the junior combination room, the postgraduate students in the middle combination room, and the faculty in the senior combination room. So if my arithmetic is correct, this means there are approximately 93 combination rooms in Cambridge, but 1 at AIMR. You may be sort of interested to see what the equivalent combination room looks like in a Cambridge college. This picture will be a little dark, but you may just be able to make it out. Slightly different setting. This is a dinner time, and these are people attending a celebration, 90th birthday celebration for one of the faculty. But it sort of shows the idea of the combination room at work, because if we go around the table, this person is in medical sciences, in literature, in history, in biochemistry, in engineering, in veterinary science, etc., in chemistry, etc. So the idea is you bring the different subjects together, which is what this room is supposed to do. You might be particularly interested in the guy at the end, who is in my college, and so is is the chemistry Nobel Prize winner for the ATP mechanism involved. So he was attending this dinner. So maybe if you turn to the Oxford English Dictionary in a few years' time, they will have to change the entry and say combination room is a name given in the University of Cambridge and at the AIMR, not just with us. So, on to the talk itself. In this audience, I hardly need to introduce a crystal, nor really should I need to introduce a glass. But the glass, of course, has in some way a disordered structure that will change its properties, and I want to make some general remarks about glasses on the various things that I have been interested in. Of course, the word glass in English normally refers to glass bottles or drinking glasses made by these well-known processes of blowing essentially a viscous liquid, very ancient technology. But in truth, you can make a glass from almost anything. You start with the liquid, that shows the volume and the temperature. You cool, the liquid may freeze to a crystal, but if it doesn't, it keeps going. As it gets colder, it becomes more and more viscous and sets into a solid glass. This picture says nothing about the chemistry of the system. So the point I want to make is that you can make a glass with almost any chemistry you like. The most common in everyday life are the oxide glasses, and of course polymer glasses are also very well known, but this talk is going to take 3 topics. It had a subtitle of structures and memory and life, and they'll relate to the 3 bottom items on this list. And we'll start with the metallic glasses. Ordinary pure elements that are metallic have extremely simple crystal structures, and their liquids have a viscosity like water, so they do not easily form any glasses. If you put in some alloying elements, you can make them form glasses, but even so you have to cool rather rapidly by rather extreme processes such as this. You might be interested that the first report of metallic glass made from the liquid 1960, here's the paper from Nature, used an even more extreme process, little splats onto a substrate, not a continuous production. This is the X-ray diffraction trace. Probably wouldn't get past the nature referees today, but it turned out to be a real result. They had made an amorphous material. That's 1960. For a long time, people were reluctant to accept that metals really could make glasses. They did not want to believe that you could get a metallic glass. And David Turnbull at Harvard was very instrumental in showing that these materials showed the same sorts of phenomena, in particular, in this case, a calorimetric glass transition, change of specific heat of the glass transition, that would mimic what you get in traditional glass systems. So people began to think that maybe these could be glasses really. When I was doing my PhD, these are figures from my PhD, it was still in some way not quite respectable to think that metallic glasses were glasses in the ordinary sense. And I could realize that oxide glasses show phenomena called relaxation, where a property, in this case the optical refractive index, changes with heating, and it changes differently at different temperatures, and you can get this situation where heating it at a high temperature could bring you to that point, heating to a low temperature could bring you to the same property value, and you would normally think that those two samples, heated at different temperatures, but with the same value of a property, would have the same structure. And it turns out they do not. If you take those two samples and you anneal them subsequently, one just carries on with the same value of the property, the other one goes through this strange thing where it appears to memorize an earlier structure, so-called memory effect. And that was characteristic of glass relaxation for oxide glasses, and we were fortunate enough to be able to show that just the same effect shows up in the metallic glasses. So it was yet another little step along the road to saying that metallic glasses are real glasses in the general family. And the other thing, of course, you'd like to do is have a glass that is not in such a tiny amount. And David Turnbull was interested in processing of materials, and he had the idea that you use fluxing, coating in a liquid oxide, turns out to be very useful in processing some semiconductors like gallium arsenide. What would happen if you used the same idea for a metallic glass forming composition, and it turns out it's extremely successful, and you can clean up the liquid metal, take out the little bits of dirt, if you like, that nucleate crystals, then it becomes much easier to make a glass. And this was up to a size of about 1 centimeter. And since that, largely through work here in Sendai, and the world of so-called bulk metallic glasses has blossomed, and you can get much larger dimensions, over 7 centimeters diameter rods in different compositions and a very wide range of compositions. So that again helps to say that these are real glassy materials that fit in the broader family. And this is how many people who work on glasses think of this world of glasses, that this is the viscosity of a system, logarithmic scale. It's liquid viscosity. This is the glass transition temperature. This is inverse temperature. So this is heating. As you heat above the glass transition temperature, the liquid has a lower and lower viscosity. But if it is something that forms a network, this is a rather straight line behavior, classic activation energy, Boltzmann law. If it's something like one of these organic liquids, terphenol, it has a very curved line, not a simple activation energy. And people think that almost any glass forming system should have a viscosity that sits somewhere in this spectrum of behavior. The question might be, where do metallic glasses sit, and where do others sit as well? And the answer will turn out to be somewhere in the middle. I think one of the most intriguing things about glasses is that it's easy to say they are disordered, and they seem to be disordered relative to the crystal. This is a simulation of a copper, zirconium, aluminium mixture, atoms of different sizes. Glassy structure certainly looks disordered. But is it really disordered? Well, it turns out not very. If you look at what helps the material to make a glass rather than a crystal, it is having atoms of different sizes. You can do this with coins. If I do a talk like this in England, it's often helpful to have an overhead projector, and I take some English coins, the 1 penny piece and the 2 penny piece. So if you have only 1 pennies, then you easily get a group of 6 pennies around the central penny. They're all the same size. If I take a 2 penny piece, it turns out that 7 1 penny coins fit round it rather neatly. And interestingly, if you do it the other way around, and you take a 1 penny piece surrounded by 2 pennies, about 5 of them fit round rather neatly. And those 5 and 7 structures cannot naturally form crystals. And you can see it's a matter of having the right radius ratio. And if you get it right, the right numbers of coins, and the right radius ratio, you get rather tight packing. But it's obviously not disordered. In fact, it's highly ordered. You can do a similar thing in 3 dimensions, and as it happens, it's rather useful in rationalizing glass-forming compositions. But I want to really emphasize this point about order. Here's a plot of the free energy, or free energy difference, between these liquids which will form glasses and the crystal. And the gradient of a free energy with temperature is just the entropy. So this is saying that this delta G value here, related to the crystal, the gradient of this line here is essentially 0, which is saying there is 0 entropy difference between the glass and the crystal. In a remarkable result, thermodynamically. So they're really not disordered at all. Indeed, you can even get some examples where this curve curves downwards, which says the glass has even lower entropy than the crystal. And that would be very interesting for the AIMR to tackle with its MathMate program, and thinking about how does one even think about entropy in a system like this that appears to be so disordered but actually isn't. Metallic glass is quite useful for lots of things because they have very high strengths. This is a chart of the elastic limit, the strength for metallic engineering materials in general, and the metallic glasses come at the top. They do also, this is of course for oxide glasses, historical picture, but you can do the same thing with metallic glasses. And maybe this is not a very interesting shape, maybe the next one won't be very interesting either, but the concept of Jan Schroer's at Yale is that you're able to make shapes with this sort of glass blowing technique that would not be accessible to metals otherwise. Whether you will actually be able to buy these in the duty-free in the airport, I'm not sure. We'll see. And work here from Japan, because the glass has no internal grain boundaries, you can pattern the surface with a very fine pattern. So I'm presenting a very positive picture. I should be honest and suggest that there might be some negative side. And the obvious negative side for glasses is that they might be brittle. So what about the world of metallic glasses? Well, earlier I was making the point about relaxation and saying that in my thesis I had taken a result from the oxide glasses and looked to see whether you could find something similar for the metallic glasses. My theme really is that it's the easiest way to have a new idea is not to have a new idea at all. It's simply to take an old idea from one discipline and move it into another, where it's regarded as a new idea. So in this case, the idea came from the world of crystalline metals. And it seemed that something was needed, because when you look at the fracture toughness from metallic glasses, are they brittle or not? They don't fit a simple category. We normally think of, in a map like this, a family of materials, like say ceramics, sits in a certain place of the map. In this case, of course, it means they're terribly brittle. Metals sit up here, they're tough. Very strangely, the metallic glasses go all the way from here to here. So from about as tough as you could get to about as untough as you could get. So how possibly to explain this very large variation?